Hi, I'm Rupesh Paineni and my teammate is Nitin Babu. We are going to talk about our ADC design project phase 1. First, we will calculate the values of capacitors. But before doing that, we need to calculate the noise at the output of the circuit. First, we will calculate the input noise from the SNR condition, and then the output noise will be input noise times the gain squared. Now we calculate the various capacitors in the circuit, and we also calculate the value of beta. Next, we do the noise budgeting. We assume that the thermal noise is half of the total noise and the static and dynamic noise are 1/4 of the total noise. Once we get the thermal noise of the circuit, we use it to calculate the various capacitance values. We need to calculate the gain and bandwidth of the OTA. To find these values, we will use the static and dynamic error constraint. The static error will set the DC gain of the OTA, which comes around 3800. Next, the dynamic error will set the value of tau, which is 1 by loop gain bandwidth. Using the value of tau, we can calculate the unity gain bandwidth of our OTA, which turns out to be 1.87 GHz. And if we assume that our OTA is a single stage OTA, the corresponding GM for the given unity gain frequency is 2.83 millisiemens. Once we calculate the OTA parameters, we will simulate the ideal OTA in the pipeline. We use a clock frequency of 64 MHz and an input frequency which is 1 by 128 times the clock frequency, which is 500 kHz. And when we perform the simulations, we see that we get an SNR of 76.95 dB when we include the transient noise. On the screen, you can see the spectrum of the transient analysis without transient noise and with transient noise. We see that the SNR is within the required constraint. Also now, you can see the plot of the settling of V reconstructed. Once the ideal pipeline simulations is completed, we will look into the OTA design. First, we need to select the topology of our OTA. There are 4 different topologies: the 5-transistor OTA, the telescopic OTA, the folded cascode OTA, and the 2-stage OTA. The first 3 options do not work out for our circuit because of the following reasons. The 5-transistor OTA has less DC gain, and the telescopic OTA and folded cascode OTA are not really good because they only allow for a lower output swing. So we will go ahead and use the 2-stage OTA in our circuit. On the screen, you can see the circuit diagram of the 2-stage OTA, of the bias current circuit, and also of the common mode feedback loop. Now we perform hand calculations to calculate the gain of the OTA and also do the frequency analysis. So we calculate the poles and the unity gain frequency. Next, we also look at the swing limit of the OTA. Once we have the above expressions, we will use GM over ID methodology to calculate the length and width of the MOSFETs in the OTA and also the bias current and the values of resistances and capacitances in the circuit. Once we complete the design of the OTA, we will simulate it. On the screen, we can see the AC analysis of the OTA. So we can see the DC gain, the unity gain frequency, and the phase margin. Next, we will look at the loop stability of the common mode feedback. We see that the phase margin is 62.39 degrees, which is greater than the required 45 degrees of phase margin. Next, we will look at the loop stability analysis of the ADC. Again, The phase margin is greater than 45 degrees, which shows that our loop is very stable. Finally, we will look at the power consumption of our circuit. The power is consumed by the bias circuit, the two-stage OTA, and the common mode feedback loop. So the total power consumed by our circuit is calculated to be 1.78 milliwatts, which is less than the required 8 milliwatts. At the moment, we have simulated the ideal OTA in the pipeline, and we have also designed the two-stage OTA. When we try to use the two-stage OTA in the pipeline, we are getting an SNR of 50 dB, which is low. So in the future, we will try to improve this SNR. Also, once we are able to make the two-stage OTA work in the pipeline, then we will work on designing the MOS switches and implementing them in our circuit.